All right, welcome everybody. My name is Noelle Walters. I'm an associate program officer with the Board on Earth Sciences and Resources. I'll be helping moderate this information gathering session this morning. I'll provide some standard introductory language that we typically give at the start of these sessions. So the task being undertaken by this committee of the National Academies of Sciences, Engineering, and Medicine is to assess potential causes, consequences, and remediation of plug failures. You can find the full statement of task via a link that I'll provide shortly in the chat. This will be largely a discussion between the committee and the two speakers that we have present with us today. So there's not a whole lot to explain about the format of the meeting, but we'll hear from our speakers, Greg Lackey, research engineer with the National Energy Technology Laboratory, and then we'll hear from Hari Viswanathan, senior scientist at the Los Alamos National Laboratory. And then we'll go into the Q&A and discussion. So this is an open on the record session, as are all of our information gathering sessions. We may address questions from anyone in the audience, but the priority of the meeting is for the committee members to ask questions to our experts. So we'll do our best to get to everyone. And I'm sure we should have plenty of time to do that, but just in case. And then to that point, I just want to remind everyone that, again, this is information gathering. So any questions that the committee asks or anything that's part of the discussion is part of that process of assembling materials that we're examining and discussing prior to making any findings, conclusions, or recommendations. And lastly, I just ask that everyone be respectful of each other throughout this meeting. Okay, having said all that, I'll do a quick round robin amongst the committee members. If you just want to give your name, affiliation, I don't know, a cool hobby that you like, if you're feeling into that, let's go ahead and do that. I'll start with one of our co-chairs, our other co-chair, Missy Feely. Unfortunately, she couldn't make it this morning, but I'll start it off with Jim Slutz, one of our co-chairs for the committee.
Hi, Jim Slutz, and what I do, my primary job is I'm the Director of Study Operations for the National Petroleum Council, Federal Advisory Committee, and I've volunteered in a number of capacities with the National Academy of Sciences and Engineering and Medicine over the years. Cool hobby, let's see, I I do so my wife and I do adventure travel. We like doing long distance hikes, some in anywhere from 8 to 12-day hikes around the world. So and we're gonna miss a couple weeks of this fun in early September as we hike the West Highland Way in Scotland, but that will be we've done various ones in Asia and Europe and other places. So
Great, thank you, Jim. I wish I could go with you. All right, let me move to Nathan Meehan.
Nathan Meehan, I'm a professor of petroleum engineering here at Texas A&M University. Let's represent. I am the greatest barbecue cook of our generation.
Bold statements being made. All right, let's move to Adam Peltz.
Hi, everyone. I'm Adam Peltz. I'm a director and senior attorney with the Environmental Defense Fund. I work on all things subsurface energy with a focus on orphan wells. And good heavens, I don't think it would be inaccurate to say that orphan wells is my hobby. I'm right now in southwestern Pennsylvania. EDF is doing intermittent surveys to find undocumented orphan wells in western Pennsylvania, and we'll be surveying the Pittsburgh suburbs this coming summer. And it's great to see both Greg and Hari.
Great, thank you. Let's move to Walter.
Hi, good morning, everybody. My name is Walter Guidros. I'm an emeritus scientist with the U.S. Geological Survey in Reston, Virginia. and also teaching on an adjunct basis at George Washington University in DC, as well as at the University of Mississippi. In terms of hobbies, I guess one of the big things, although I haven't worked on it lately, is genealogy and working on tracing family roots. I think I've gotten back to the mid 1500s in Switzerland. I'm still searching to try and get back even farther.
Wow, that's really impressive. All right, Tom Kropatch.
Noel Tom Kropatch, Director of Wyoming Oil and Gas Conservation Commission. Hobbies, I guess, just anything outdoors and the wide open spaces of Wyoming. Thanks.
Thank you. Eilish?
Hi, Eilish Rosenbaum. I also work with Greg Lackey at the National Energy Technology Lab here in Pittsburgh. I'm a research engineer as well, and I'm a project leader and a portfolio leader. And as far as hobbies, pretty much anything outdoors I like to do, but this time of year, I like to do whitewater stuff. And so we've been getting lots of rain. So one of the few people that is happy when we have rain. So, and snow. So
Great, thank you. Jim Bolander?
Jim Bolander, good morning, everyone. Consultant, have worked a lot with Adam at EDF. Probably our main hobby is travel. Our trip so far this year, helping our kids move, but we also did Mammoth Cave National Park. So trying to hit as many as we can.
Thank you. I'll introduce or Cameron, do you want to introduce yourself? This is my colleague. We co-lead this study together.
Hi, I'm Cameron Osfig. I'm the Director of the Board on Infrastructure and Constructed Environment at the National Academies of Sciences. My hobby is home project woodworking.
Ooh. All right, let's go to David, and then we'll have Mary introduce herself.
Hey, good morning. My name is David Perrin. I'm a wells engineer for Chevron in our global well abandonment group. I support our legacy P&A projects, both Gulf of Mexico and U.S. land, as well as CCS ventures, looking at the legacy wells and screening them. In fact, I remember meeting Greg last year at one of those conferences, so it's good to see him again. And my biggest hobby right now is I have a 2-month-old daughter, so trying to, getting sleep is a good hobby right now.
Fair enough. All right, Mary?
Mary Tang, Associate Professor, Civil Engineering at McGill University. Hobbies, I do a lot of hiking with my family, yoga. Oh, actually, I have one. Lately, I play a little piano, and we like going to music shops to buy different sheet music and different versions of it, different editions of sheet music. So I've collected a lot.
Very nice. Thank you all for sharing. All right, let's go ahead and move to Greg Lackey, if you'd like to introduce yourself and go into your verbal presentation, and then we'll go to Hari.
For sure, Noel. Hi, everyone. Greg Lackey, research engineer at NETL. I think I've met most of everyone here either at the workshop last year or other venues, Dave, like I guess that was an SPE workshop last year. As far as interesting hobbies go, we've got little kids, so I feel like David's comment resonates well. Those hobbies go out the window. But I guess I would say gardening. I really do like gardening. Last year, I tried to grow a really big pumpkin, and I got it to 200 pounds. So about 1/10 of the size that the champion growers get. I'm certainly humbled by the experience. So stuff like that. It's a good time, and Pennsylvania is a good place to do that. So I guess for my presentation today, I know last year at the workshop, I kind of gave an overview, and I tried to synthesize a lot of different people's work, kind of in the space of well integrity, especially when it comes to like factors that influence well integrity, impact well integrity. A lot of my work over the last, I guess, decade has really focused on analyzing publicly available data sets, right? So I guess my two core skills are data analysis and numerical modeling. So, you know, what we've tried to do is find data on well integrity in different publicly available venues, and then try to see that, you know, analyze these data to understand just different phenomena, like how frequently wells experience integrity issues, what types of integrity issues they experience, and then, you know, potential implications for things like groundwater, or, you know, it's some of the other projects here at NETL, things like carbon storage, hydrogen storage, natural gas storage, so on and so forth. So I thought for my presentation, the format that I'll do here, well, I guess, I don't know, Noel, I can share my, if I could share my screen, it looks like screen sharing is disabled. I do have papers that I can kind of walk through key figures of, if that's all right.
Yeah, that'd be great. And you should be able to share your screen.
Okay, so let me know if everyone can see this paper here.
Yep, we can see that.
Right. So this was something that I worked on, I guess, at the beginning of grad school. It's a study led by Owen Sherwood, who's now a professor at Dalhousie University in Halifax. And essentially what we were looking at here is the baseline groundwater quality sampling data set from, I guess, the Colorado ECMC, used to be the COGCC. In the state of Colorado, they require operators to do groundwater sampling of homeowner water wells near new wells that are proposed, right? So at the time, I guess this was around 2016 is when we published this, and we were working on it probably starting in 2014, 2015. There was a big expansion of unconventional drilling in Colorado, especially in the Wattenberg field, which is what I'm showing here. And so we had this fairly large data set. You know, there's in the Wattenberg field, over 50,000 oil and gas wells, over 35,000 water wells. And what we wanted to understand was, you know, things like Gasland, these types of very high profile documentaries were coming out. We wanted to understand how folks were getting methane in their drinking water and what the origins of that methane would be in the Denver Basin. And for anyone, I guess, unfamiliar with the geology of the Denver Basin, there's a number of these bedrock aquifers. You can kind of see them colored here. They kind of lie on top of the Pierre Shale, which is a really low permeability unit that stretches a couple thousand feet down to the producing reservoir. So not as complex as the geology of Appalachia, where I know a lot of folks on the call have worked. And in a way, you know, we did a pretty thorough analysis of the isotopic signatures of methane in coals and other potential sources. And the story on the Front Range is rather straightforward. So there's microbial methane in the shallow aquifers that you know, as you go with depth to deeper formations, it transitions to thermogenic. So in most cases where we were seeing thermogenic methane in people's drinking water, you know, it was pretty clear that this was coming through a well in some way. So as a part of the study, we found 32 cases at the time that were documented where thermogenic gas had been, I guess, detected in a homeowner well. Maybe they filed a complaint, something like that. And that was, you know, in total 42 water wells that were impacted. So about 0.12% of the water wells in the region were experiencing this. We knew that, you know, this is likely underrepresented. You know, if you go back in time to like the 80s, there's newspaper articles from the Denver Post about this issue. So it's something that kind of has been ongoing as long as oil and gas drilling has been taking place in the region. But I would just highlighting this because this was really the motivation for my work, was to understand, well, what is this pathway, right? Like, how is methane getting from these deep, you know, Niobrara Shale or J Sand or one of these deeper formations? How is it leaking upward into these drinking water aquifers? So ultimately, what we ended up doing was diving really into the well construction data in the region. The Colorado regulatory agency does a really fantastic job with making data publicly available. They essentially at least have most of their well completion reports, plugging reports, all that kind of key information available and accessible in a digital format. So we were able to pull a lot of that down. We started looking at the ways a lot of these wells were built. So what I'm showing here is just some cross-sectional diagrams of different well configurations. Most of the unconventional wells that they were drilling in the early, I guess by 2014, 2015, they were cementing to surface, right? So you've got of course, your production casing, and they were bringing this cement all the way up to surface. But a lot of the older wells in the region, they were cementing, they're just complying with regulations, which essentially said you have to, cement a few hundred feet above the deepest oil and gas bearing zone. A lot of times that's the Sussex or Shannon formation, and they essentially would cement above that, and then they would leave this annulus uncemented, which has some potential benefits, right? It lets you kind of have eyes on the well. You can see if you end up developing some type of, if gas is moving along the well in some way, you can detect that. And then what we showed in this study too is that pressure at the top of the cement does matter for the leakage rate. So having a column of drilling mud or fluid actually can help in some circumstances minimize the leakage rate. So the study I'm highlighting here, what we did was we kind of dissected all of these different well diagrams, and we built a numerical model that simulates gas flow through a dry cement, and then multi-phase flow so through this kind of open annulus. So it was kind of a coupled model, and the whole idea was trying to simulate sustained casing pressure buildup. And a lot of this work was led originally by Andrew Wotanowicz at LSU. He and his graduate students wrote a number of papers on this for sustained casing pressure issues offshore. They did really fantastic work, and we certainly built on top of that work and tried to focus on this in an onshore context. And the takeaways were that essentially what happens in these wells is if you have a faulty cement seal around the production casing, or maybe an unknown intermediate formation, gas can enter this annulus and migrate to the surface. In Colorado and a lot of US states, we keep well annuli closed. What happens is that pressure builds and it can displace the fluid in the annulus. And what we were seeing, what we hypothesized as the pathway was that a number of operators were potentially letting their wells develop pressure greater than the hydrostatic pressure at the bottom of the surface casing, and that was kind of inducing gas migration out the bottom of the surface casing. So we modeled this pathway. We showed that if you have an uncemented annulus like this, you're going to build sustained casing pressure until you exceed the hydrostatic pressure at the bottom of your surface casing if you have a continuous leak, right? But if you are sealing the bottom of the surface casing with cement, that's a closed vessel, and that pressure will actually build and kill the pressure gradient along the cement, and ultimately the leakage rate will reach a steady state. You'll get a steady state pressure at the wellhead, which a lot of the studies of the offshore sustained casing pressure showed that. So I think everybody on the call is familiar with terms like sustained casing pressure, surface casing vent flow, but essentially that's gas leakage along this annulus that can occur from some type of a well integrity issue. So once we understood, I guess I'm going a little bit out of order, but once we at least conceptually understood this pathway, the state of Colorado requires routine well integrity testing. It's now required for every well in the state. And these tests, I'll throw the caveat. I know this is a plugging well, I guess, abandoned well workshop and an abandoned well information gathering session, but these are all performed on active wells. So just keep that in mind. But they do routine testing for things like sustained casing pressure to monitor the integrity of wells. And at the time, they had set up a testing zone, I think in 2010 or 2011. That's what this grid is here. So we had about a couple thousand wells that were routinely tested there. And to the credit of the operators in this region, they were doing more testing than was required by the state. And especially one of the big operators in the region kind of established it as a best practice. And we found a pretty large data set there. So what I'm showing here is, wells in green. These are wells that, built what we called in this paper critical sustained casing pressure. Essentially they build enough pressure to exceed the hydrostatic pressure at the bottom of their surface casing. And then these wells in gold, these were ones that actually had a surface casing too shallow to protect the deepest aquifer in the region. So that's the Laramie Fox Hills. I guess, on the Front Range, there's always a need for more water. So we continuously drill deeper for water. And a lot of these wells, they were built in a time when they weren't drinking out of the Laramie Fox Hills. So one of the, we had a couple figures in here to kind of help illustrate this concept. And I think this one here kind of captures it. We were looking at vertical, deviated, and horizontal wells. Like I said, unconventional drilling was kind of the motivation at the time. And what you can see here is that while a lot of these newer wells were developing higher pressures in their surface casing annuli when they were experiencing integrity issues, a lot of them did have deeper surface casings, right? And it actually turned out that it was these older wells with shallower surface casings that were developing kind of an overpressure in their annulus. We were able to find like a number of cases where these were implicated in some of those incidents that we reviewed that I reviewed in the first paper. So coming up through this point, that kind of completed a lot of my graduate work and got me really interested in like, well, can we expand on this? And how many other states in the US do this type of testing? So this is a paper that we put out this year with some colleagues in Germany. They were interested in reviewing well integrity monitoring practices across the world, right? And then I got involved to bring in kind of the North American perspective. And I guess right away, what you'll take away from this is that it's a patchwork, right? So in the US, each state manages their own oil and gas regulations, right? And every state here in green, I think I got the numbers over here. I guess 19 of the 33 states have annular pressure or flow monitoring requirements in some form. Most of them require annular pressure monitoring only really during hydraulic fracturing. And that makes sense, right? You're going to be pressuring up the well. You want to make sure that, your integrity is intact, that you're not, pushing fluids into your annuli when you're fracking the well. But others kind of have these situational requirements, these 7 other states. So some of them have specific circumstances when you would want to monitor your annular pressure. But there's really only 4 states that have routine testing requirements. So that's Colorado, New Mexico, Pennsylvania, and Texas. And of those 4, really only 3 of them, Colorado, New Mexico, and Pennsylvania, publicly report these testing data. So, there are some flow monitoring requirements, like Pennsylvania. They kind of leave it up to the operator's discretion whether or not you leave your surface casing annulus open or closed. But ultimately, most states are monitoring for annular pressures. And I would say when you start getting into flow monitoring, like states like California, they start, they have like a leak detection and repair program. You actually see some of that type of monitoring coming under like a different agency. So like Colorado, they do some greenhouse gas emissions reporting and monitoring, and that's the Colorado Department of Public Health, right? So now we end up with like different data sets and different people kind of working with these different data sources, right? So at least in Colorado, we've mostly worked with data from the ECMC, and they're looking at pressure data for well integrity purposes. I know that they're now doing some measurements of emissions from wellheads, things like that might capture a continuous leak. But again, it's kind of a different jurisdiction, things like that. So once we understood which states had requirements, we kind of zeroed in on Colorado, New Mexico, and Pennsylvania because they were making their data publicly available. And I know tables like this are a lot to take in, but I guess I wanted to highlight that just because you have an integrity testing requirement doesn't mean that it aligns between states, right? So there's a lot of heterogeneity here. So there are recommended practices. So API RP 90-2 is a recommended practice from for for managing annular pressure in onshore wells, right? And New Mexico's approach mostly aligns with that. Colorado has some slight deviations. Pennsylvania has even more deviations from that. So with this study, which we published in 2021, we were aggregating all of this testing information and trying to put it on a level playing field so that we could compare apples to apples. It was really challenging, right? Like, essentially, if you were going to follow API RP 90-2, you would have a lot of data. You would essentially be setting a threshold pressure. If that pressure is exceeded in the annulus, then you'd be doing a bleed off test and recording those pressures as they bleed down. and then you'd be shutting in the well annulus and monitoring pressures for another hour or half hour and recording that as well. We didn't have that level of information. So what we did was we tried to follow API RP90-2 as best we could when we interpreted the data, even if we had to look at like the results of multiple tests. So like in Colorado, for example, they don't do a build back test. So, you know, if a well doesn't bleed to zero, then we consider it to have sustained casing pressure if it's over our threshold. But you know, if it does bleed to zero, then we look at the next test, and if it's back above the diagnostic threshold, then we consider it to have sustained casing pressure. So I'm just saying this to emphasize that we did our best to follow industry standards here to understand which wells have a continuous source of you know, typically methane, sometimes brine, and other fluids leaking through the annulus causing sustained casing pressure. And ultimately, you know, our takeaway from this study was that, you know, frequencies of integrity issues vary over a pretty wide range. So, you know, here I'm showing on the right, this is the percentage of tested wells with sustained casing pressure or, you know, some type of flow through the annulus. And immediately you'll notice, like up here in the Wattenberg, I think at the time, again, this was prior to testing on all wells. We had about a quarter of the wells that they were testing in this region with sustained casing pressure indicating an integrity issue. Whereas down in the Raton Basin, which, you know, they were requiring complete testing for all coal bed methane wells, it was, I think, 0.3%, right? So geology comes into play here. The coals in the Raton Basin are shallow, and there's not a big pressure drive for fluids to migrate along wells. And, you know, we weren't seeing a lot of these types of issues there. Whereas, you know, up in the Wattenberg, we had kind of the geologic conditions and clearly some integrity issues that were arising that was causing a much higher frequency of integrity issues. So after we did this study and we saw how much things varied over a wide range, we decided to focus in on one area. And we chose to focus back in on the Wattenberg field. That's probably the area that, you know, I know the best, and I'm most familiar with the data and the geology in the region. And at this point, it was now, you know, we had data through the end of 2019. And after our 2017 study came out, I know Adam on the call worked a lot with the well integrity regulations in Colorado, and they passed Senate Bill, I guess it was that 181, that required all operators to perform this testing in the state. And as a part of that, they were setting new detection thresholds for pressure, and they were requiring sampling of surface casing fluids, which, you know, geochemical sampling of surface casing fluids. So that really created a really rich data source of well integrity information. And so we were able to come back to the Wattenberg field. I think in this study, let's see, how many tests? We had 2,573 geochemical gas samples. I guess geochemical gas and water samples collected in, we'll call this the greater Wattenberg area. And what you're seeing here is we also, you know, anything in blue, these are surface casing samples. Anything in orange are just production samples, and green, these are wells that had both surface casing and production samples. So it's a really, really rich data set. And, you know, they were requiring isotopic analyses of the hydrocarbons in the gas. So it is, there's a lot that you can do with this type of data set. So I won't go, you know, I think I only have 20 or so minutes, so I won't go into the details of all of the isotopic analysis. But ultimately, like I said, we had the full suite for, you know, hydrocarbons, C1 to C5, delta 13C measurements. So we were able to use things like a Chung plot here. What we're showing, these are the averages for the different producing formations. And then these are the microbial signatures from the shallow aquifers. And then this is kind of a density plot of all of those surface casing gases. And you can see most of them are aligning with production gas, but there are variations. You know, we do get shallow gas into surface casings. And then, you know, this was kind of our best estimate for the signature for the Pier Shale. And then if we go down, you can kind of see this is another really standard standard plot for interpreting the isotopes of gas. This is the composition. So this is methane over ethane and propane. So it's just a ratio where essentially microbial gas will have a lot fewer higher chain hydrocarbons than thermogenic gas. And again, this kind of emphasizes that, in gray, you're seeing these are surface casing gases, and most of them were aligning with the signature of thermogenic gas. So ultimately, what we found is that 96.2% of the wells sampled in the Wattenberg field had thermogenic gas present in their well annuli. And of those, we were able to look at cementing records, and we had so much production gas data that we could kind of interpolate surfaces, because everything, of course, varies in space, right? There's a hot spot in the field that changes these signatures. So we were able to interpolate a surface of the signatures for production gas from different producing zones. And we did our best, to associate specific surface casing gases with a producing formation, and then look at those specific wells and see where their cement tops were. And we found that, about 73% of these wells had cement above the formation where we thought the gas was from. So I think that really highlighted to us that, like, clearly there are some challenges here with cementing in the Wattenberg field, and that a lot of these gases are probably migrating upward through something like a microannulus, right? And there are intermediate formations where gas could be bleeding in, but I think a lot of the time here we're looking at gas. It might not be from the target zone, right? It might not be like if you're targeting the Niobrara, maybe it's coming from the Sussex or Shannon, a shallower interval. But most of the time, these intervals were cemented. So this approach allowed us to identify that that's really what we thought that integrity issue pathway was through those cements. So then the last thing that we did was, we came back to the Wattenberg field again, and we looked at the pressures and the geochemical samples, and we tried to come up with a better estimate, right? So I think in our 2021 study, we estimated about a quarter of the wells in the region had integrity issues. But since that time, they required testing on all of the wells. And we were seeing that, in the greater Wattenberg area, if we look at geochemical analyses and we look at pressure analyses, 17% of these wells had, they met the API criteria for having sustained casing pressure. So that, that's a much lower estimate than what we had before. So there was clearly a lot of wells in the region that were not experiencing integrity issues, that weren't doing integrity testing before that requirement came into place. And then, from the thermogenic gas samples, I've talked to ECMC about this. 2019 was the first year that they required it. So I think that there was a bit of a gap between, uptake with the new regulation requiring the surface casing gas analyses. So I'm on my to-do list is to go back and look at this data set again. But at the time, only about 8% of the wells had like a thermogenic gas or oil confirmed in their surface casing annulus. So there was a bit of a gap between what we were seeing with pressures and what we were seeing with geochemistry. But the whole idea here was to build this data set and try to understand, well, what's causing these issues, right? And I'll say, we focused in the paper on the results for sustained casing pressure because it had a much longer testing history. We had a lot more pressure data, and that went back all the way to 2010, and even a bit before. But when we ran these models and these analyses for, wells with thermogenic gas and or oil in their surface casing annulus, a lot of the trends were the same, right? So I do think that the two data sets support each other. But what we saw here, one of the more interesting things in this study, which came out earlier this year, is, we performed a hotspot analysis. So this is a geostatistical technique to identify where I guess the way we did this was we broke this all up into grid cells, and we were trying to find statistically significant clusters of higher percentages of wells with sustained casing pressure compared to its neighbors. And this red outline here is kind of where we see this hotspot of integrity issues. And it really pops out, and it follows what these dark black lines, these are the wrench faults in the region. So this is the Longmont wrench fault. And, I guess there's analyses of the geology in the region. They've documented some increased fracturing along the Longmont Wrench Fault. And what's really interesting is, of course, the rivers follow these kind of fault lines. So these are the St. Vrain and South Platte River Valley. And that hotspot kind of lives in this river valley here. And we see this kind of increase in sustained casing pressure. And then we also have this little arm out into the center of the field. And this is pretty close to where the geothermal anomaly in the field is. So there's a hot spot in the field where you have higher pressures, overpressured zones in formations like the Codell. So this was the biggest signature that we saw when we did this data analysis. And then, we had 20,000 wells. We built a machine learning model using, ensemble decision trees. It's a, XGBoost is a really common algorithm that people win competitions with, whatnot. So we put together over 70 attributes of oil and gas wells, everything we could amass. And ultimately, the model, I guess the ability of these models to make predictions, right? I won't go into the details of it, but when we gave it everything, the model was performing fairly well. It was performing better than, of course, random guessing, and it was performing better than if you use like the hotspot analysis technique. And it was also performing better than like what the regulators did originally, which was like kind of draw a box and require people to test there. So it certainly was pragmatically useful, but it wasn't perfect, right? We weren't making like 100% predictions of which wells were going to have integrity issues and which wells weren't. And when we teased apart which, well attributes were contributing to these issues, it was almost impossible to tease out spatial information, right? So, in the first version of the model, we included information about nearby wells that had integrity issues and the distance between wells, things like that. And of course, it used that right away. We know the integrity issues are clustered, and that it's a strong clustering in the region. So the model would just rely on that. So if we remove that information, that's what you're seeing in B here. Then, of course, it relies on things like longitude and ground elevation, which is exactly what you'd need to find the hotspot in the field, right? Because we know it's at lower elevation, and you can use longitude to kind of move around the field or distance to a river. So then if we removed all that, then the model was relying on operator, which, there's one operator that owns a big portion of these wells in the hotspot. But, if you dive deeper and you look at all of the operators that have wells in the hotspot, we see this effect where it's almost a doubling or tripling of the percentage of wells that have those integrity issues. So I don't believe that it's, one operator's practices causing this hotspot. It's clearly, it's an effect that's felt by all operators with wells in the area. So, ultimately, like I said, I think the biggest takeaway that we found was that there is a geologic component here. That's correlation, right? We didn't tease out causation, but it does seem like it's pretty strongly correlated with geology. And, we can see in the Wattenberg Field and other regions, like the Lloydminster area of Canada, right? There's these areas where we know these integrity issues occur frequently. And I think obviously geology is having some role to play here. We hypothesized subsurface fracturing from the wrench faulting was potentially the cause, maybe make it harder to get a good cement job, so on and so forth. But ultimately, we just don't have enough data to make perfect predictions here, even in a state like Colorado that has all these data. So, Noel, how am I doing on time?
This is all really interesting, but yeah, I think if this is a good pause point, we
I
should
could stop.
Okay.
Yeah.
Yeah, no, thank you so much. That was really thorough and informative. But
Sure.
yeah, let's hold our questions. And I realize I forgot to put the full description of the committee's charge into the chat, so I'll just do that now. Apologies. And members of the audience, if you have questions, please use the Q&A function. And again, we'll try our best to get around to you. And yeah, why don't we turn it over to Hari, if you want to give an introduction of yourself and then move into a verbal presentation.
Yeah, sure. I'm Hari Viswanathan. I'm a fellow at Los Alamos National Labs. And I guess for hobbies, tennis, wildlife photography. So last summer I went and photographed mountain gorillas and chimpanzees in Uganda. this September going to Indonesia to photograph birds of paradise. And so, yeah, looking forward to that. I'm sort of jumping into this for the first time with this panel. I mean, I know when we've had previous occurrences of this, I always thought Greg is the one best aligned for the wellbore integrity piece that is sort of the charge of this panel. So Greg, I got to make sure, have you told them about catalog and all this sort of stuff completely? Or,
I haven't. I saw you were on
context.
here, so I was focusing on well integrity.
Okay.
I figured you would focus on catalog.
Okay. Yeah, and so first I'll just talk and then I'll put up my screen. But yeah, I actually have a background in wellbore integrity. I mean, I've been doing quite a bit of modeling in subsurface systems and wellbore integrity for carbon sequestration and things like that. I've been in my career probably for the last 30 years. But for for orphan wells, basically DOE stood up a program called Catalog, and what the idea of that was to take 5 different national labs and sort of have them come up with best practices, see what different states are doing, and basically transfer knowledge, for example, from one location to the next. What are the kind of cutting edge technologies that we have to help identify and characterize undocumented orphan wells? And so Adam and Mary have, know about this effort quite a bit, and they're even like co-authors and so on. But I think the wellbore integrity piece that you're interested in on this panel, fits right under the characterization part of our charge. And so what I thought I would do is just at least lay out kind of a high level publication that we did, which Mary's actually one of the co-authors on that kind of lays out what Catalog is doing, and then sort of maybe try to put like some of the wellbore integrity stuff in context. And so let me see if I can successfully share my screen. I think everyone can see it.
Yep, correct.
And so the general idea behind Catalog is because in the previous administration, quite a bit of money was given to the Department of Interior to basically, plug and abandon orphan wells. And the question is, how can you do that in the most efficient way possible? And so as part of that, the Department of Energy was given funding to sort of help develop best practices and so on, both in the area of identification and characterization. And I'll sort of point out that it's always been a pretty bipartisan effort in that sense, because people have these scattered across the entire US, and, our program is still going now. And what this paper kind of lays out is, the different things we work on at a high level with respect to trying to identify and characterize the undocumented orphan wells part of this program. And so when we started this, one of the important things that we thought we had to do is just try to understand what the different states thought were their biggest data needs. I mean, what did they actually care about, and so on. And so the IOGCC is quite good at conducting surveys. And so we had them conduct a survey on what they thought about undocumented orphan wells, kind of what are their data needs and so on. Because one of the kind of criticisms that when we look at ourselves, is we're just sort of scientists that like to do really cool stuff. And so if you give us drones and AI, we'll probably just go and do some impractical thing with drones and AI. And so we wanted to make sure we were grounded in something that people actually cared about. And what better way than just ask a bunch of people what they thought. And so, in terms of biggest data needs on, undocumented orphan wells, I mean, maybe it's not particularly surprising, but definitely mechanical integrity, which definitely comes into the charge of this panel, is one of the things that comes up. I mean, just knowing where they are is probably the number one thing. And then the thing that we found kind of interesting is just approaches to trying to find these wells how much people were not really relying on any high tech, even magnetometers, because if you look in the literature, which is what our team would typically do, we would be kind of looking at the more R&D aspects of this problem. But historically, people have been looking at historical records. And so Greg's actually been kind of on the front lines of a charge to automate, being able to scan in historical records and use optical character recognition to digitize it and to use AI to extract the necessary information. That's one of the tools that's come out of our program. And Greg's done really great work having different people actually use the tool and test it out, and see how useful it is. How can we improve it? Another thing is these wells are often just found by landowner complaints. And, just for example, the current administration cares quite a lot about this because orphan wells greatly reduce property values and also make it pretty difficult to use the land if they're littered with orphan wells. And then field inspections. But if you see what's really not on here is, to a very high extent, is sort of like, flying over with drones and using multiple sensors. And, that there's been a lot of advancement worldwide in that area, a lot, as well as with our team. And so we've sort of focused on things like that. And then, I guess as far as how high of a priority are undocumented orphan wells, compared to other things. I mean, I think it was a little harder to kind of interpret this one, right? Because, but I would say people did still think they're, something that they definitely worry about. And then, bottom line, what are the factors for ranking wells? I would say our team also has looked at what different states have been doing when they basically prioritize these wells and what are the actual regulations in place, comparing and contrasting different states and what do we think are good, good practices and how can we transfer knowledge and things like that. And so that's sort of how we started out the program. And then basically we've ended up going with it. And I probably am not going to take up all of my time because what I don't want to do for this panel is just kind of in case, and so it's probably better to leave it up to questions to make sure everybody is satisfied. So, for us, I would say so far we have been much more focused on just finding the wells and improving how to actually find them, right? And so that includes, like I was saying, digitizing the old records. We've been investigating using, instead of just quadcopter drones, which don't stay up in the air for that long, can we use a fixed wing drone that can stay up in the air for like 8 hours? And can we use, multiple sensors on those fixed wing drones, both like LiDAR, magnetometer, and then AI has gotten so good at being able to extract signal from noise that we really think we could identify way more wells, undocumented orphan wells, than was possible before, just because of advances being made worldwide on AI and drones, which we can just leverage. And so that's what we've been doing in that extent. And then, there's sort of a citizen science aspect to this too, because we learned that a lot of people just find these in their backyard and so on. So having an app and basically being able to have people report what they think could be an undocumented orphan well and being able to check these things out more. But I think what's the interesting part of this and why I'm particularly interested in this panel is since characterization is part of our charge, and so far a lot of our work has been more on the identification side, even though in my previous work I've done plenty of characterization. What kind of characterization should we be thinking about for our program? Because we know plugging and abandonment companies have pretty set practices when they actually get to a well and how they plug it. And then Greg's done all the kind of great work he talked about in detail before. And I know this panel knows more about characterization than myself. But, since we're also supposed to do some level of characterization when we find a new well, what is the appropriate level of characterization to do, before you actually can get into some sort of prioritization scheme and hand it over to a plugging and abandonment company? So that's something we're still trying to flesh out. And so I'm just going to kind of go through this in since I can't give an official presentation, but this is published work already. But this is just sort of work that basically shows if you just use one sensor like magnetometer, but if you do magnetometer and methane together, and if you combine that with AI, the more sensors, the better. And sort of the takeaway message for this, which is in a lot of branches of science right now, is that we're learning from how nature does things. And so, for example, there's been some research which is very different on how is it that dogs smell so amazingly well? I mean, what is it that they're able to do? I'm out on the walk and my dog goes and stops in some location, and you're always wondering, what is she seeing? And most people know they can smell a lot better than us, but what is it that lets them do that? And my assumption was always they just have a much better sensor to be able to smell things. But there's more research going out that it's not necessarily one type of sensor that lets them smell things better. It's just that they have a bunch of different types of sensors in their nose, and they integrate all that information, and they're able to almost get like a visual picture of smell that's well beyond what we can do. And so for us, especially in the subsurface, which tends to be very data sparse, or trying to find a well that's buried and there's no signature at the surface, the more signals, because they're all noisy, but if you combine these noisy signals, the sum is much greater than the individual parts. And so combining AI with drones and multiple signatures is something that we think we can have a ton of impact on. And we do have a section in this paper on what we're starting to do with characterization, both from the methane perspective or leakage perspective. And the idea here is just, is there an easy way to sort of approximate concentration, of what's coming out of these wells? And I'm not going to get into detail on that. And then also just kind of what would be the first cut, without going and doing a really expensive characterization when we do find a well? Is there some kind of simple acoustic method to at least tell us something about the well at a high level that sort of helps us get into what we're doing? And so this table, I think, kind of summarizes a lot of the different things we've been trying to do on catalog. And so for the identification piece, which I'm kind of calling well location here, I would say using optical character recognition and large language models, that's the kind of stuff Greg's been heading up, and I think that's been highly, highly successful. And so since this paper has, been published, I think it's well beyond the proof of concept stage. It's almost at the rollout stage. As far as using computer vision, just looking at old USGS maps and so on, and being able to just automate and pull off where there might be wells so we can do a better investigation. AI is great at that, and I think we've gotten pretty far on that. The citizen science aspects is still in its early stages. I think the multi-sensor data fusion with machine learning is definitely advancing incredibly fast for us. And then we are pretty happy with the fixed wing drones and their capability of being able to stay up for so long and basically being able to detect things, especially when you combine it with AI. And then I think what's more aligned with this panel is just the characterization pieces of this. And if anything, I would say we're still trying to flesh out what is our role here, because it's not, we're not the plugging company for sure. We're just kind of the ones that have found what could be a new orphan well and what level of characterization makes sense. And so actually getting information from this panel is something that we would be interested in. So acoustic methods, and then time domain reflectometry. And then, as far as the emissions part of this, how do you actually figure out if something is leaking, how do you get a concentration measurement without having to, set up a flux tower and things like that? And then I think we're going to be getting into a lot more of the subsurface impacts of a well leaking as part of the prioritization. That's something we haven't done yet, but definitely I think that's kind of the direction that our program is heading towards. And so, I mean, hopefully that was kind of short and sweet and not too off of what this panel is actually interested in, but definitely the output of what we want to develop are tools that we're graded on, that we develop tools that people will actually use. We cannot just develop things, that are just fun and cool and gets us into a good journal, but then no one uses it. And so we're definitely have a lot of people looking over our work to make sure people use it. And so, Greg's tool is getting used. And then we've got other ones as well that are definitely along that way. Other part of this where I think we can actually be highly impactful is just best practices. I mean, not necessarily even what our program's doing, but just learning, you know, like Adam's talking about Pennsylvania. I mean, Pennsylvania has been dealing with orphan wells for so long, and they've done so much great work there. Just simply, you know, being able to summarize that and transfer it to other states and making people aware of it. So, you know, why reinvent the wheel? I think that's another place where we can be super impactful. So our outputs are best practices and tools. And I think what is really exciting about this program for me is it's still incredibly sciencey because the tools do take advantage of AI, which is changing at remarkable speed, and drone technology, which is changing at remarkable speed, and optical character recognition. So there are quite a few cutting edge things that we can deploy that you need to deploy to make this happen. And so I think that's why it's been one of the most fun projects I've been on, and you know, it's continuing. And so I'll stop there.
All right, thank you so much, Hari. That was absolutely very relevant and informative for this committee's charge. Thank you so much. So I think we'll move to discussion and Q&A. And I want to start off with the committee, open it up to you all if you have any clarifying questions or comments for Greg and Hari. Walter, go ahead.
Hey, thanks, Noel. I have a few questions for Greg, and I'm not hugely familiar with the geology around Wattenberg, so I was wondering if you could clarify a few things perhaps. So when you mentioned the wrench faults, how laterally or vertically extensive are those faults, and how much work has been done to characterize what those faults are like? You know, are these really abrupt boundaries, or is there significant fault gouge, and are these transitional type faults? Just looking to get a better feel for what the actual faulting systems look like.
Yeah, Walter, that's a great question, and I think the fact that I'm an engineer is going to show through, and that I'm not a geologist. So
That's okay.
I don't have a lot of those answers at the top of my head. I mean, I think I did my best to kind of review the literature that were out there on the faults, and other than some kind of fundamental papers on the basin that are probably from like the 70s, and I know the USGS did quite a bit of work. I think trying to think of her name. I had a heck of a problem with my memory in recent years, but yeah, I think Deborah Higley, I think with USGS did a number of nice studies on those, and I could pass them along, Walter. And like I said, I haven't seen anything that dives into really extensive detail on kind of some of your specific questions, but I mean, they have been studied quite a bit for the the geologic context of the basin.
Yeah. And so I guess as an alternative to faulting, is there any potential correlation you could see between localized changes in porosity or permeability or the rock characteristics or anything else that might allow for alternative pathways for methane or methane leakage?
Yeah, so I mean, there's no, if we're looking at the producing formations and pathways to the shallow subsurface, really that pure shale that's in between is, if you look at a core of it, it's kind of like plateware, right? Like it's very, very impermeable. So I mean, I guess there is a potential that some of these faults might be extending all the way up, and
right.
But the fact that I mean, yeah, I certainly think what that might look like, if it's not cement, maybe it's a fault connecting from deeper into a shallower portion of the well, but even a lot of these wells have cement to surface, right? So at some point it has to be moving along those well bores to show up in the surface casing annulus. So yeah, we don't have high quality, as far as from the reservoirs themselves. I'm sure the companies do, but at least in the public domain, ran out of those type of data, or I would have tried to include more of that in the model. I think most of the data that we put in the model was, information about the wells themselves, and even like cement information, right? Like we just really know the cement top. We don't even know the type of cement, things like that. So we are, like I said, I feel like I've worked a lot with state databases. Colorado is definitely one of the best. And even there, having the type of data that could help us dive deeper, we're limited. But I would love to have a deeper dive on the geology front. I think, that'd be interesting. So.
Do you know if the faults are still active? Are they moving?
No, I mean, there's really no, there's no very little seismic activity in the region or things like
Okay.
that.
Okay.
I did include things like seismicity in the study. There's been some very minor seismic events kind of in the northern, like, I guess I'm not sharing my screen, but kind of that outside of the Wattenberg field up north. I know they had some kind of induced seismic events when I lived there from, they do a lot of wastewater disposal in the region, but
Okay.
Nothing major. And there was really no correlation between these issues and things like seismicity.
Okay. The paper that you referenced, where is that? Is that publicly available?
Yeah, so the last paper that shows the hotspot, that came out in the International Journal of Greenhouse Gas Control, and I can share all of these papers. They're all publicly available.
Okay, great. Okay, great. Thank you so much. Appreciate it.
Yep.
Thank you, Walter, and Greg. Mary Kang?
Yeah, thank you for the really nice presentations. Yeah, I have two questions for both. Noel, can I ask both two questions or? Okay.
Sorry, go ahead.
Okay, yeah, so thank you for that to both of you. Yeah, well, I'll start with kind of a broad question for Hari first. I really like your point about looking more at subsurface impacts and roles. So can you talk a little bit more about that in terms of what kind of tools? Is it, I guess it's more monitoring focused, and will it be like at the wells or more at potential receptor sites? So if you can talk a little bit more about that, that'd be great.
Yeah, so I mean, I think that, I mean, at the highest level, we kind of know if there's a well that's leaking gas, that fluids, even though they're slower, there is a pathway, right? And then we also know that there's multiple wells in a particular area. And so being able to distinguish between, how much is something actually impacting groundwater and things like that are definitely a difficult thing to do. And so I think we're sort of trying to leverage, this kind of, we feel like we're getting a lot of improvement in being able to take dynamic measurements, whether it's subsurface or atmospheric, and being able to say a lot more of, interpret that dynamic data and get better characterization using things like AI and so on. And so we want to try those type of tools to see if it, if we can actually show. And so we're sort of looking for, kind of like a test, like good tests where we can actually validate like such an approach. And so basically what we would want to build off of is this is sort of the standard statistical techniques that have been used so far. And now if we bring in something that takes advantage of more dynamic changes and things like that, are we able to improve, our detection capability, right? Because I mean, the AI stuff's not magic at all, right? It's just trying to do better on the signal to noise ratio on the measurement that you're trying to get. And so we have techniques that we can deploy, and right now we're trying to figure out exactly, where can we try it? And right now we're allowed to work where we've already been working, but not necessarily at new sites yet. And so we're sort of trying to wait for some of that stuff to loosen up so we can try some of these things out, if that helps.
Okay, no, that's very interesting. I'd be very interested to see what you
We should
guys deploy and where.
Yeah,
and where to deploy these groundwater monitoring tools. Because I mean, there is one section on groundwater monitoring that's part of this report. So this is very relevant. So if you any kind of high level overview of the potential tools, and is always helpful.
So I mean, there's a review paper that I did on like in reviews in geophysics, which is on like the state of the art on subsurface fractured systems, and there's a whole thing on how there have been major advancements on the observational science, and it talks about these dynamic techniques. So I think it was just like 2 years ago. So
okay, yeah, please, if you could share that with Noel, that I really appreciate that. Thank you. And I'm going to ask kind of a similar question to Greg in terms of the groundwater part, because, with the Colorado study, you see a lot of interesting results, and which can be also translated to groundwater, and even with your latest study. So that's in one location.
Yeah.
And you did talk about, the challenges of kind of using that information to get a sense of what's going on elsewhere. But maybe you can talk a little bit more about how best we can interpret that, your results, to think about the problem at a national scale.
Yeah.
And I mean, you've done some well integrity comparisons between Colorado, Pennsylvania, so you have some insight. So if you can talk a little bit more about that.
Yeah, I mean, I think at the national scale, right, like, at least what we saw with the 2021 paper is that, integrity issues vary really widely, right? Like that no one well is the same. And, the geology is unique in each region. And I mean, you see this in Canada, right? Like there's, some areas that have issues more frequently than others. So, I mean, when you think about the Front Range, right, what do we have? We kind of have a nexus of perhaps a unique geology that's causing challenges for well integrity. And then we also have regulatory and kind of, I don't know if it's regulatory or more like social factors where, people are drilling deeper for groundwater, and there's a lot of water wells in the Laramie Fox Hills now. And I know you've done some studies of this in California, right? Where when you keep going deeper, right, how you built something previously no longer protects that. So I think that Wattenberg field is interesting because it is an area where we've kind of had this nexus of challenges, the societally we're changing how we're using groundwater, and, these older wells, like we had this issue with the integrity issue. So, I mean, when we analyzed wells in that 2021 paper, which had pressures high enough to overpressure their surface casing annulus, a lot of them were in the Wattenberg. Well, so across all of Colorado, most of them were in the Wattenberg, and there were very few in New Mexico, right? And then we couldn't do the analysis in Pennsylvania because we didn't have surface casing depths. So I would say I know these issues happen in Pennsylvania and other regions in Appalachia. One of the studies, there's a great study by Samuel Harrison from like the 1980s where they looked at this problem in northeastern Pennsylvania. So it's ongoing. I would say as far as groundwater impacts go, though, my intuition from all of these great groundwater studies that happened around the 2013 to 20 whatever era when we were really looking at groundwater impacts from unconventionals is that these issues happen for sure. It's not ubiquitous. It's not like every single well, right? Like there seem to be these clusters like Dimock, PA, right? Like we know there's something going on with the geology in Dimock, and there's a number of water wells that have had a lot of increased methane from that. So I think that's the takeaway, is that you kind of need the nexus of a multiple factors, right? I think if a well is built to have a surface casing that protects the drinking water, and you're monitoring your integrity, like, you certainly can prevent groundwater impacts, right? But there's kind of some of these areas where there's, perhaps, outdated or older wells that don't have those types of protections, and newer water wells that were built that weren't considering that, and you kind of have those types of issues. So I don't know. I get the sense that, places like Pennsylvania that have more complex geology, we saw about 14% of wells with integrity issues, but we know there's a lot of compliance issues with the data set that we've studied in Pennsylvania. So I can't, it's probably around that number. We've done a more recent analysis of integrity issues in New York, and we've seen kind of lower frequencies there than we saw in Pennsylvania. And that was with compliance inspections that operators were performing. That's not published, but ultimately I would say that like between that 5 to 15% range is probably where the percentage of wells that experience these issues, and then it's a much smaller number that end up contaminating groundwater in some way. So I don't know if that gets at your question, Mary, but
no, that's really helpful. Maybe I can just do a quick follow-up and
sure.
With your New York work. The before you went to New York and looked at New York, you've studied Pennsylvania, New Mexico, Texas, and Colorado.
Yeah.
Given the, your intuition or what you learned from all of these places, are you surprised or not surprised about what you see in New York?
Well, I'm not
Sorry, that
surprised.
was
I'm not surprised because to be honest, a lot of wells that with deviated well bores have sustained casing pressure type issues, right? So whenever we analyze the larger data sets, we do see an effect where deviated wells, especially ones built at the beginning of the unconventional boom, were having integrity issues more frequently. And in New York, we don't have those wells, right? So we have mostly older vertical wells. And the testing data we looked at went back to, I guess 2013 or 2014 to today, or to last 2023. So it's about 9 years of data. And they have a lot of really old wells, right? So I think there's, again, if you've depleted the formation, there's no pressure drive. Like, I guess I would kind of expect to see lower frequencies of those types of integrity issues. What we didn't have is, an analysis. We don't have actual pressures, right? A lot of those, they actually vent surface casings in New York. So a lot of those are, inspectors saying like there's flow between these annuli, right? So we don't see pressure build up as much as we do like in Pennsylvania, or, especially the Western states where they close well annuli. So I think, yeah, I wasn't surprised to see the frequency. I didn't think it was, super surprising. It was kind of similar to what I've seen across a lot of these studies. Again, non-zero, but not as high as, say, like a place like the Wattenberg field where we know we have issues. So.
Oh, great. Thank you.
Yep.
All right, thanks so much. Let's go ahead and move to Adam and then David.
Great, thanks. And I'm afraid I also have two questions. So the first one is to either or both Greg and Hari, thinking about plugged well failures, which neither of you covered directly, but I imagine that you think about that as, subtur crosscut and that sort of thing. If there's anything you want to share about rates, causes, vintages, or geographical hotspots, that would be great.
Adam, I think about it. We don't have data on that at the scale that we've looked at. Right. So, I mean, you certainly see studies where, I know Eilish was involved with an effort from DEP where they've gone out and inspected older wells that are plugged to see if there's gas migrating. I know there was a study in British Columbia that came out recently where they've looked at this. I'm hesitant to put a number on it because I don't know what that number is. We've looked a lot, I guess that other hat that I wear, David and I met in the world of carbon storage, right? Like we've looked a lot at well plugging schemes and, diagrams for things like screening for carbon storage. And, we do see that, plugging practices vary a lot over time, right? So we see a large variation in that. And, there's certainly, especially if you're looking at future use of the subsurface, it seems like most regulators are moving towards thinking about reservoirs as a resource, right? But yeah, I would say plugging practices have improved over time in general. So, my gut would be that it'd be older wells, but I think we say that about everything. We say that about well integrity issues. We say that, right, a lot about this type of stuff. So without hard data, I can't put a number or percentage on it.
Yeah, we have a researcher that's sort of trying to look at this at least in a modeling perspective because, it's hard to constrain. But yes, we know that older wells probably are, probably not plugged as well. But then if it's an undocumented orphan well and it's in some field where the pressures are very much depleted, then there's not nearly as much of a driving force, right, for things to leak a great amount. And so even though like the interference between multiple wells and things like that have been done to death for active wells, and the oil patch, right? The industry looks at that quite a bit. We kind of feel like for orphan wells, it's actually not looked at as much because one, it's not the current well practices, but then also the gradients may be a lot lower. And so those are two canceling effects. So they're trying to at least do kind of like proof of concept modeling to try to understand how it compares to the current literature in active wells.
Great. And that's in fact consistent with what we've been hearing throughout this process. And my second question is about finding wells through buildings, which is starting to happen with drone magnetometry. And I wonder, Hari, if you have anything to say about that and any guesses about how many wells there might be under buildings. I have a guess, but I'll see if you
Yeah,
do.
I mean, one of our teams has been working in fairly dangerous areas in Los Angeles, trying to figure this kind of stuff out. And yeah, a lot of the tech, I mean, I guess the lessons at the project level for me is there's certainly no one size fits all strategy to detect these things because, in downtown Los Angeles where there's tons of these things, and they've been having to do almost like a door to door kind of thing. And most of the technology that we have has, one, it may not be effective, but two, it's also walking around with that technology in parts of downtown Los Angeles, sometimes doesn't go over so well. And so, yeah, it's actually something that the LBNL team is definitely digging into because they're starting to do all this stuff in downtown Los Angeles. But yeah, I think there's no jury out yet, but I definitely could talk to Sebastian, about his latest findings. I haven't asked him lately, other than just the anecdotal stories of this is what happened when I went here. Like I didn't know what you just said. I didn't know you could do the magnetometry through the buildings, for example. Like I thought it would be a lot less sensitive.
Parsons has done it, and we're trying to do it here in Southwest Pennsylvania. So we can catch up about that some other time. But I
Yeah, for
appreciate
sure.
it. Seems like an interesting emerging issue. Thanks.
Yeah.
I have just a quick
I think it's
follow-up.
a big. Sorry. Yeah.
I'm sorry to interrupt. And I apologize, Hari, if I missed this during your presentation, but is the LBNL team that you mentioned doing like sort of door-to-door work, is that also part of the individuals leading the citizen science efforts, or is that different?
No, that's different because
Okay.
the citizen science effort is there, actually it's with University of Colorado because they have
Okay.
like a kind of a well finder app, that was for
Right.
other stuff. And so they're really good at developing apps. And so we wanted to leverage what they've already done for this app to kind of move it over to orphan wells. And
Okay.
again, it got off to a much slower start than other areas because, for example, there's just all sorts of questions like we don't want to be asking somebody to do something unsafe,
Yeah.
right? Like right next to a well, and so it took quite a bit of time to sort of get the thing launched, like what are the boundaries of what we can actually do. But it is moving forward because I think it's a pretty important part of this for us.
Yeah, and do you know so far whether the respondents for that app are largely like, large landowners or people in like cities or more densely populated areas? Do you have any like sense of that so far?
So one, the app doesn't exist yet. We're building
Oh,
the
sorry.
app, but
Okay.
based on our survey kind of stuff,
Okay.
right? I mean, I can't give you quantitative numbers, but I mean, it sort of did feel like these were out in the fields, like people are just finding these things,
Okay.
much more
Gotcha.
than city. Yeah.
Okay, understood. Yeah, thank you for that clarification. I'm really excited. My background's in sociology, so I get really excited about citizen science efforts. So I just wanted to ask a couple clarifying questions
Yeah,
about
I mean,
that.
I'll also say we have students working this summer kind of looking at the intersection of where all these wells are in Los Angeles and how it intersects with, GIS is perfect for this, right? Like how does it intersect with public schools and,
Right.
all these other things, because I think even from a property value perspective and an economic perspective, this is a very big deal, but we need to be able to quantitatively show that. And so we're trying to up our GIS game in that sense.
Okay. All right, thank you so much. Sorry, before we get to David, Greg, I think you unmuted yourself. Did you have anything to add?
I was just going to add about the building thing. Like, I mean, Adam, I know you've talked a lot to Natalie and Rick Hammock and those folks here. I think in like 2016, they did Rick and Garrett Belosky here looked at legacy wells in Versailles. which is gotta love how Pennsylvanians say certain words. But yeah, Versailles, Pennsylvania, they did this analysis, and they might have considered finding wells in buildings in that study. So I don't know if you've seen that one. I think it was like a technical report or something, but yeah, it might be useful.
Great. I'll check up on that. I think they call it Versailles in many states, by the way.
Yep.
All right, thank you. Let's go to David. Thanks for your patience.
No problem. It's Versailles down here in Louisiana.
There you go.
And I'm gonna keep on the theme of 2 questions only because Adam's question on the plugged well failure kind of triggered something in my mind, and I appreciate the comment of, we just don't have the hard data, and that is obviously the finding that we're coming to that realization as well as a committee. However, what you do have with everything that you shared is on the wells that are still standing today that we can monitor, that we can have lots of data on the integrity issues that are happening today. Is it fair to assume that, if you don't remediate those, because eventually these wells will have to get to the P&A queue and be plugged, and if you don't remediate faulty annual cement that is channeling and causing migration, or those same causal factors can lead to causal factors of when the well is plugged and capped and cut and buried and out of sight, out of mind, can cause the same migrating conditions can occur depending on geology and how much sustained casing pressure and all
Yeah.
those type of things. So I guess, how can we maybe translate the 30% of these wells that exhibit these issues and all? We like to think we're going to remediate all those before it comes time to permanently abandon them, but it could be those wells were still constructed that we've already since plugged and no one's really watching. And I think goes into the question is, should we be doing long-term monitoring and not, and how big of a
Yeah.
it's not zero, but it's not 100% either. And how can we get to be strategic where we need to put monitoring versus even if that is happening, we acknowledge that it's insignificant. So that's the struggle I have, certainly on trying to
Yeah.
answer that question.
Yeah, I think, David, I mean, you're on point here, right? Like, if we're seeing, let's say, across most regions, somewhere between 5 and 10% of wells with sustained casing pressure. And then, I mean, I know you've looked at these old plugging records. They're not putting rock-to-rock barriers in these wells. A lot of times they're putting plugs just in the production casing. Maybe they're pulling some casing, putting some plugs, get a surface plug in. So if that cement was able to transmit, gas for how many years, right? I assume that it can still transmit gas, right? And if they didn't, go in and, try to remediate the annulus in that well, upon plugging, right? So I think we're certainly now to the point where regulators are having an operators check to see if it's got sustained casing pressure. It's increasing the cost of P&A jobs. I'm sure it's making it more problematic, right? But yeah, I would think for a lot of older wells, they weren't doing that. At least from the record, and I mean, this is heuristic. I don't have hard data on this, but in the areas where we've looked at plugging records for things like carbon storage, a lot of these older wells, they're not putting that, they're not going in to remediate an annulus when they plug this, which, obviously if you want to use the subsurface in the future, right, that's a huge challenge. But I guess that would be my question is, if you're going to deploy resources to monitor or whatnot, most of these leakage rates are really low, right? Like I do think like we're seeing, Mary knows far more about this than I do, but it does seem like, for most of these wells with sustained casing pressure, they're building pressure rather slowly, right? These are not really, really high leakage rates. So then it becomes kind of that triage question of, well, how do you know which ones you want to monitor, and is it every well, and so on and so forth. So I think your brain is going the right place. Like, certainly we might not know how many wells have faulty plug jobs, but the annulus is a leakage pathway, and we have info on annular cement, at least in modern wells. So, I guess that would be my question: is if that gas pressure has depleted over time, is it still pushing a lot of gas? Is it a small amount of gas? What is it? So, yeah.
Yeah, it's the whole, what is long term, what is forever, eternity, things like
Right.
that,
Right.
I think it goes to, point forward, we know more than what we know now, and we need to be able to resolve those vessels that is knowingly causing issues. But it's certainly, it's a hindsight question too. So I appreciate that response. And then the other question would have been for Harry, Ahari. It's on, if I'm a plugging operator, a plugging company, what do I need to help characterize, especially when it's a well that's undocumented. So by definition, we don't know anything about it other than, hey, there's casing sticking out the ground. We found it by a magnetometer, or maybe it's buried, but from the surface on down, I don't know how deep it is. I don't know what casings may still be in place or not be in place. Is there anything the labs are doing? I know from our standpoint, we're working to maybe partner with the Colorado School of Mines Multiphysics Consortium to take magnetic inversion. So when you do the drones, aerial drones, it's obviously got a magnetic anomaly, but you don't know if it's 5 feet below ground or 200 feet if you don't have the record. So we're looking at, can it tell me where the top of the casing, if they were cut below ground, which a lot of times were done in World War II era, or for whatever reason for salvage, and then can it tell me size and diameter. So if it's do I have a 5-inch casing within a 8-inch casing within a 10-inch casing to help? Because eventually, if I'm a plugging engineer, I need to know what am I about to get into, or am I going blind, or can I recreate the schematic, which doesn't exist in some form or fashion. So don't know if anything's working there, or if that gives an idea of where maybe we can go with some of the new technology.
No, I think we should chat. Our approach so far in this has been two-pronged. So there's a characterization work package, which Andrew
Okay.
Delore had. And so he's done two things. He basically has interviewed, I don't know, about 5, 6 drilling company people, right? To sort of ask
Okay.
them, what do you need, right? Like from us. And then he sort of has something kind of similar to you, but we're not that hopeful of being able to do much from the drone level. But we're kind
Okay.
of hopeful that at the surface, like kind of walking around, that there could be acoustic techniques, like pretty simple acoustic techniques that could give you, a first cut at the kind of stuff that you're talking about. So I think we should probably talk, because there's probably a lot of overlap in the ideas. But so far, yes, we've sort of gathered information on what, like, I don't know, 5, 6 different people think we should try to do. And then we've documented all of this to try to put together kind of like what our charge should be. And then based on our sensitivities, definitely from a fixed wing drone, it's just not going to happen, because I mean, those are flying like 40 meters up and they're just don't have the sensitivity. I mean, quadcopter, I don't know. We're also not that optimistic, but walking on the ground, we are optimistic that we could come up with some pretty cheap solutions. And so that's kind of where we're at. And almost things like hitting it with a hammer and seeing what signal comes back, like
Yeah.
low tech, because we're pretty sensitive to, coming up with some fancy schmancy thing that no one's going to use, right? We need something that anyone's willing to use that gathers some good first order information.
I'm gonna break my rule, and I'm gonna go with 3 questions. So to follow up on that with the acoustics, and I don't how familiar, but can it also, because we also heard from Pennsylvania there are issues where they're basically re-entering wells that didn't have any casing, so they're going through a very large uncased open hole wellbore to get to what is attainable depth, or TD, to where the producing reservoir was. That's how they produce it, was without production casing or anything like that. But and maybe it's very geology sensitive, but we may have something similar to that, to like in Gulf Coast states, where it's the whole, and probably Greg knows this too in the CCS world, is we look at all these old legacy wells in a site we want to do CO2 storage, and a lot of them are uncased open hole, so we can't even really fix it, but it's right through the injection zone. But there's a lot of work and done on, did the hole collapse and seal, like self-healing of holes, and could this the acoustic things that we're doing to help characterize orphan wells may help with the prioritization? Is, yes, it's there, it's an orphan well, and it's been there for a long time, but is it really causing issue, and do we really need to spend the money? Is there anything to work? And that's what I'm saying, is maybe is there some tools to help prove up the sealability? And I know it definitely goes to, if you're in an undepleted or severely depleted geologic zone and all, just looking at that risk profile of, really, can it leak or will it leak into the future?
So we're totally on the same page, but we
Okay.
just don't have it. We don't have anything yet, though. I mean,
Okay.
that is
No.
what we're working towards.
Okay. Good deal. Well, thank y'all.
All right, everybody. Thank you so much. We're coming up on 11:30. It seems like there are no remaining questions or comments. But I'll give it a moment in case anybody does. If not, thank you, Greg and Hari, so much. This was really informative. You gave thorough presentations. And yeah, this is really helpful information for us to have. I'm sure we will be in touch in the future as well. So with that, yeah, just thank you everyone so much, and I'll let you all go. Have a great rest of your day.
Thanks, Noel. Thanks, everyone.
Thank you.
Yep.
Bye-bye.
Thank you, everybody.
Thank you.